Okay, let's finish up our graphing of our 6 basic trig functions. We have 2 more to go, the secant and the cosecant functions. Notice in the homework for section 4.4, I just say know the graphs of the basic secant x and cosecant x function. We could do all the translation, the shifting left and right and up and down and reflections, but we're not going to do that here. This is a service course, not a science majors course. But I just want to expose you to the graphs so you can say you've seen them. So I want to first construct the graph of cosecant x using the graph of sine. Remember, we did the same procedure in the last section with using the fact that tangent and cotangent were reciprocals of one another to get the graph. We're going to do the same thing here. So first I want to start with the sine graph. Let me do that in blue. And we know what the basic sine graph looks like. We've done that before. Let me get a better blue marker here. All right, so every pi over 2, something important happens on the sine graph. And again, sine, the range runs from -1 to 1. And we know that the sine graph crosses the y-axis at 0, 0, and when we add to the right, we go up. Low, middle, high, middle, low, middle. Okay, so there's the sine graph that we already know. Okay, now we're trying to construct the cosecant graph. Cosecant x. Now remember, sine and cosecant are reciprocal functions of one another, so we can use that fact to construct the cosecant graph. We could make a table. Let me just show you what I'm doing here. For example, we know that sine of pi over 2 is 1. We did that before. Sine of pi over 2 is 1. Well, what would the cosecant of pi over 2 be? Well, sine and cosecants are reciprocals of one another, and the reciprocal of 1 is 1 over 1, which is also 1. So the point pi over 2, 1 is on the graph of the sine function. The point pi over 2, 1 is also a point on the cosecant function. So that point stays the same. Likewise, if you take sine of minus pi over 2, I'm going to change this here. Sine of minus pi over 2 is -1. Well, cosecant of negative pi over 2 would be the reciprocal of this answer, which is also -1. So notice this point, minus pi over 2 minus 1, is a point on the sine graph and the cosecant graph. Likewise, so is this point. So notice if I continue this graph on, every high point on the sine graph, every maximum, is going to be a point on the cosecant graph. Every minimum value on the sine graph is also a point on the cosecant graph. So you might think, well, geez Louise, is this just going to be the same graph? Well, no. Let's focus on where the zeros are. Let me just I'll pick pi. So if I take sine of pi, well, according to the graph, sine of pi is 0. Well, let's do cosecant of pi. Well, cosecant is the reciprocal of the sine value, but 1 over 0 is undefined. So just like with tan and cotan, wherever the cosecant function is undefined, we have a vertical asymptote. So we're going to have a vertical asymptote on the y-axis because sine was 0 there. We're going to have a vertical asymptote at pi because sine is 0 there. We're going to have a vertical asymptote at minus pi because sine is 0 there. So you see the graph of cosecant is looking quite a bit different than the sine graph. Now, if we do what we did before with the tan and the cotan, we know that the cosecant's undefined at pi. What's happening near pi? So pi is 3.1415926535. So if we pick a value just to the left of pi, say 3.14, notice sine of that is very, very small. What's the cosecant of 3.14 going to be? Well, it's 1 over sine of 3.14. Again, 3.14 is not exactly pi. It's a little less than pi. So if we type that in again, make sure you're in radian mode. So 1 divided by sine of 3.14 is almost 628. So notice when I pick a number very, very close to pi, and to the left, cosecant of it is huge. Well, what if I pick a number here? So I know what's going on near pi. What's happening near 0? If I pick a number just a little bit bigger than 0, say 0.01, let's take the cosecant of 0.01. So I'm picking a value just to the right of 0. What's the cosecant of that going to be? Well, that's 1 over sine of 0.01. And if we type that in again, make sure you're in radian mode, 1 over sine of 0.01 is 100 point something. And notice that point is way up here. So you see what's happening, we're getting values on both sides. When we did tangent and cotangent, on one side of the asymptote we had a large value, on the other side we had a small value, a really negative value. Here they're both very large. And if you do the same thing over here, you're going to get a negative value here and a negative value here. And so you see what's going on here. When the x values get close to 0, the y values blow up. And when the x values get close to pi on the left, the y values blow up. And you get something like this. And likewise, same thing down here, but it blows down. And same thing. Now, I often will have students say, oh, the parabola here and the parabola here. Now, these are not parabolas. Remember, a parabola goes up and out forever. And notice these are trapped in between two asymptotes. So they go up forever, but not out forever. So I just refer to them as cups. So we have a down cup and an up cup and another down cup. So you see the pattern with the cosecant graph. Every pi over 2, something important happens. But notice how it alternates here. We have asymptote, point, asymptote, point, asymptote, point. Now that sounds like the same pattern we did for tan and cotan, but remember for tangent and cotangent, it was asymptote, point on the x-axis, asymptote, point on the x-axis. Here, it's asymptote, point at -1, asymptote, point at 1, y value is 1, point, y value is -1. So what you have to remember here is what does the cosecant graph do on the y-axis? Vertical asymptote. And when you go to the right of it, you have the bottom of the up cup. So if you can just remember that, vertical asymptote, bottom of the up cup, vertical asymptote, top of the down cup. Again, you can always visualize the sine graph here. But remember, so let me erase this and just construct the cosecant graph from scratch to show you how I do it without sketching the sine graph. So if I'm sketching the cosecant graph, something important happens every pi over 2. I know the cosecant graph has a vertical asymptote on the y-axis. I know I have important values of plus or minus 1. And that goes asymptote, point, asymptote, point, asymptote, point, asymptote. So the places I've left out, I have a point. When I go to the right of the asymptote on the y-axis, I have the bottom of the up cup. And so this point here is the top of the down cup. And over here we have another down cup. So if you just remember the pattern, and remember vertical asymptote on the y-axis, and the up cup is to the right, that's what the cosecant graph looks like. Is the graph of the cosecant function periodic? Yes, we have a repeating pattern. Down cup, up cup, down cup, up cup. So it is periodic. Now the question is, what's the period of the cosecant graph? Well, clearly, if you want to get the entire pattern to repeat, you just can't go from, say, minus pi to 0, because that's just a down cup. If I move that over, there's no down cup. The pattern doesn't repeat. To have a repeating pattern, you have to have a down cup and an up cup. So if I go, say, from minus pi to pi, and I move that over, notice it'll match. The down cup will match with that one. And from minus pi to pi, that's a distance of 2 pi. The period of the cosecant graph is 2 pi. That should not surprise you at all, because the cosecant graph is related to the sine graph. That's not a surprise. If we were going to do all the stuff we did in the previous sections, the shifts and the period changes and that sort of stuff, well, how many pieces would we use here? Well, just like the sine, I think of the down cup as being in 2 pieces and the up cup as being in 2 pieces. so I will use 4 pieces. So let's just briefly talk about if we did change stuff. So if I multiplied the trig function here, the cosecant function, by like 6, what would that do to the graph? Well, the sine graph that sat here in the middle, that would change the amplitude to 6, which means this would get larger. So it's a stretching function, vertical stretch. So instead of being at 1, the up cut would be starting at, it'd be at 6 and go up this way. This would be at -6. Negative, multiplying by negative would do a reflection. That's nothing new. What if we have a number multiplied by the x? Well, that would change the period. You would take the old period, 2 pi divided by b, take 1/4 of the period for the pieces, just like with sine and cosine. Okay, so now let's do the same thing for the secant graph. I don't think the answer is going to surprise you here. So y is secant x. So I'm going to start by constructing the cosine graph, because cosine and secant are reciprocals. So pi over 2, pi, 3 pi over 2, 0, minus pi over 2, minus pi. I just randomly pick some numbers. And cosine crosses the y-axis at 0, 1. And we have a middle, a middle, a low, a middle, middle, low, middle high, middle, low. So here's our very rough sketch of the cosine graph. Well, if we argue the exact same way we did before with the cosecant graph compared to sine, well, everywhere that cosine is plus or minus 1, secant will also be the same value. Because the reciprocal of 1 is 1, the reciprocal of minus 1 is 1. And everywhere cosine is 0, secant is going to have a vertical asymptote. And just like we did before, if you pick a value close to pi over 2 here to the left, notice cosine of that number of the angle is very, very small. So when you take the reciprocal of a tiny number is huge. And notice both of these numbers here, the y values are small, so when you take the reciprocal, they're going to be huge. And not surprisingly, you get the up cut here, you get a down cut here, and you get a down cut here. So it's just like the cosecant graph, except for the asymptotes and the cups are in different places. So notice here, the secant graph crosses the y-axis at 0, 1, just like cosine does. And as soon as you realize that, you know it's the bottom of the up cut. So it's point, asymptote. You know that's the bottom of the up cup, so then the top of the down cup goes in. Now for the secant and the cosecant graphs, it should not surprise you. Maybe the cups surprise you, but it shouldn't surprise you where this graph exists. Notice it's from -1 and down, and 1 and up. It was the same for the cosecant graph. That should not surprise you, because remember when we did the ranges of the trig functions, sine and cosine were trapped between -1 and 1, including -1 and 1. And secant and cosecant could be -1 to 1, but anything less than that, -1, or greater than 1. And so it shouldn't surprise you that there's no graph strictly between -1 and 1 for secant and cosecant, because secant of x equals 1/2 doesn't make any sense. Secant of x equals 0 doesn't make any sense. And so that's why there are no points on the secant graph here. Now, is the secant graph periodic? Yes, it has a repeating pattern. The period, not surprisingly, is 2 pi. You need a down cup and an up cup. Notice from minus pi over 2 to pi over 2 to get an up cup and a down cup is 4 pi over 2, the distance, and that's 2 pi. And not surprisingly, we would do 4 pieces. I think of this as half of a cup, half of a cup, half of a cup, half of a cup. That's 4 pieces. And again, so if we multiply by a constant, that would make, if I multiply by 4, the bottom of the up cup would be up at 4. It would be like this. This would be a -4 going down. Change the period, same way multiply by a number in front of the x, like a 5x. You would take 2 pi divided by 5, and then multiply by 4 to get the pieces. But I'm not going to ask you to do that. All I want you to know in this section is what does the basic secant graph look like, the black graph here. What does the basic cosecant graph look like, the one we did before? So basically on a quiz or a test, I would just say, what is the graph of y equals secant x? Write it down. What is the graph of y equals cosecant x? Write it down. Just the basic trig functions. So that's all I expect you to do in this section 4.4.